So I have the function g here. It's expressed as a fourth degree polynomial. And I want to think about the intervals over which g is either concave upwards or concave downwards. And let's just remind ourselves what these things look like. So concave upwards is an interval. An interval when you're concave upwards is an interval over which the slope is increasing, and it tends to look like an upward opening U like that. And you can see here that the slope over here is negative, and then as x increases, it becomes less negative. It actually approaches 0, it becomes 0, then it crosses 0, it becomes slightly positive, even more positive. So you can see the slope is constantly increasing. And if you think about it in terms of derivatives, it means that your first derivative is increasing over that interval. And in order for your first derivative to be increasing over that interval, your second derivative, f prime prime of x, actually let me write it as g because we're using g in this example. In order for your first derivative to be increasing, let me write this. So concave upward means that your first derivative increasing, which means that your second derivative is greater than 0. And concave downward is the opposite. Concave downward is an interval, or you're going to be concave downward over an interval when your slope is decreasing. So g prime of x is decreasing, or we can say that our second derivative is less than 0. And once again, I could draw it on this. So when x is lower, or it looks like we have a positive slope, then it becomes less positive, and then it becomes less positive, it's approaching 0, it becomes 0, then it becomes negative, and then even more negative, and then even more negative. So as you see, our slope is constantly decreasing as x increases here. So in order to think about the intervals where g is either concave upward or concave downward, what we need to do is let's find the second derivative of g, and then let's think about the points at which where the second derivative can go from being positive to negative or negative to positive, and those will be places where it's either undefined or where the second derivative is equal to 0. And then let's see what's happening in the interval between, and then we'll know over what intervals are we concave upward or concave downward. So let's do that. So let's take the first derivative, g prime of x. It's going to apply the power rule a lot. 4 times negative 1 is negative 4, x to the third power, plus, okay, so you're going to have 2 times 6 is plus 12, x to the first power. I can just write it as x. And then minus 2, I could say minus 2x to the 0th power, but that's just minus 2. And then the derivative of negative 3 of a constant is just 0. And now I can take the second derivative, g prime prime of x is going to be equal to 3 times negative 4 is negative 12x squared, decrement the exponent, plus 12. And so let's see, where could this be undefined? Well, the second derivative is just a quadratic expression here, which would be defined for any x. So it's not going to be undefined anywhere. So interesting points where we could transition from going from a negative to a positive, or a positive to a negative. Second derivative is where this thing could be equal to 0. So let's figure that out. So let's figure out where negative 12x plus 12 could be equal to 0. See, we could subtract 12 from both sides, and we get negative 12x squared is equal to negative 12. Divide both sides by negative 12, you get x squared is equal to 1, or x could be equal to the plus or minus, or x could be equal to the plus or minus square root of 1, which is of course just 1. So at the second derivative at plus or minus 1 is equal to 0. So either between plus or minus 1 or on either side of them, we could be concave upward or concave downward. So let's think about this. And to think about this, I'm going to make a number line. Let me find it a nice soothing color here. All right, that's a nice soothing color. And let's say, actually make the number line a little bit bigger. So there we go. Let's utilize the screen space. And so if this is 0, this is negative 1, this is negative 2, this is positive 1, this is positive 2. We know that at x equals -1 and x equals 1, our second derivative is equal to 0. So let's think about what's happening in between those places to see if our second derivative is positive or negative. And from that, we'll be able to say where it's concave upward or concave downward. So on this first interval right over here, so this is the interval where we're going from -infinity to -1. Well, let's just try a value in that interval to see whether our second derivative is positive or negative. And let's see, an easy value there could be -2. It's in that interval. So let's take g prime prime of -2, which is equal to -12 times 4, because -2 squared is +4. So it's -48 plus 12, so it's equal to -36. The important thing to realize then is, well, if over here it's negative, then over this whole interval, because it's not crossing through 0 or it's not discontinuous at any of these points, that's why we picked this interval, that over this whole interval, g prime prime of x is less than 0, which means that over this interval we are concave downwards. So concave downward, concave downward. Now let's go to the interval between -1 and 1. So this is the open interval between -1 and 1. And let's try a value there. Well, let's just try 0 will be easy to compute. G prime prime of 0. Well, when x is 0, this is 0, so it's just going to be equal to 12. The important thing to realize is our second derivative here is greater than 0, so we are concave upward. Concave upward on this interval between -1 and 1. And then finally, let's look at the interval where x is greater than 1. So this is the interval from 1 to infinity, if we want to view it that way. And let's just try a value. Let's try g prime prime of 2, because that's in the interval. And g prime prime of 2 is going to be the same thing as g prime prime of -2, because whether you have a -2 or a +2, you square it becomes 4. So you're going to have 4 times -12, which is -48, plus 12, which is -36, which is -36. And so once again on this interval, you are concave downward. Now I graphed this ahead of time. Let's see if what we just established is actually consistent with what the graph actually looks like. We were able to come up with these insights about the concavity without graphing it, but now it's kind of satisfying to take a look at a graph. And actually, let me see if I can match up the intervals. So actually, this is pretty closely matched right over here. And so this is, actually, let me make it a little bit smaller. All right. And so let me move my bounding box. So I'm saying that I'm concave downward between -infinity, all the way until -1, all the way until this point right over here. So all the way until that point, and that looks right. It looks like the slope is constantly decreasing all the way until we get to x equals -1, and then the slope starts increasing. The slope starts increasing from there all the way, and right at x we're transitioning. So I'm going to leave a little, I won't color in that. And so here our slope is increasing. Do that same color. Our slope is increasing all the way until we get to x equals 1, and then our slope starts decreasing again, and we get back into concave downwards. Whoops, I want to do that in that orange color. We get back into concave downwards. So what we were able to figure out by just taking the derivatives and doing a little algebra, we can see quite clearly looking at the graph.